In this video, we are going to look at binomial probability experiments called Bernoulli trials. In some probability experiments, the results for each trial can be reduced to two outcomes, success or failure. The following statements represent the criteria required for a binomial probability experiment. The experiment is performed a fixed number of times, n. There are only two outcomes for each trial, success, given by lowercase p, or failure, represented by lowercase q. The probability of success must be constant for each trial. The random variable x counts the number of successful trials out of n trials. The binomial probability model is represented by the following formula. The mean is found by n times p. The standard deviation is found by the square root of n times p times q. Let's use this example to answer some questions about binomial probabilities. We'll work them out first by hand, then again using a TI-84 graphing calculator. A college student is interested in finding out whether the incidence of left-handedness is greater in creative people. Using the results of previous research, which indicates left-handedness is present in 1 out of every 10 people, she randomly surveys 20 out of 500 art students. Assume the frequency of the trait has not changed. First, let's find the mean and standard deviation of the number of left-handers in the group. The mean is given by the formula n, our sample size, times p, our probability of success. Our sample size is 20. Be careful, our sample size is not 500. The problem states she randomly surveys 20 out of 500 art students. So 20 is the sample size we'll be working with. The probability is 0.10, or 10%. This is the probability of success. In other words, the probability of being left-handed. We know this due to this statement. Using the results of previous research, which indicates left-handedness is present in 1 out of every 10 people. That's 1/10, which is 10%. Now I simply multiply these values together and get a mean of 2. So the mean number of left-handers in this group is 2. Now let's find the standard deviation. The standard deviation is found by taking the square root of n, our sample size, times p, the probability of success, times q, our probability of failure. In our case, this will mean taking the square root of 20 times 0.10 times q, our probability of failure. Well, if our probability of success is 10%, and we know that the sum of all probabilities in a sample space must sum to 1, then the probability of failure must be the complement to the probability of success, 0.90, or 90%. Our standard deviation works out to be approximately 1.34. Next, let's calculate some probabilities. What is the probability that our student finds left-handedness in none of the 20 students that she surveys? In other words, we're looking for the probability that no students are left-handed. Probability of our random variable x being equal to 0. we set up our equation. Using the binomial theorem. The probability of success is 0.10, and we're saying that none of the students are left-handed. So that's 0.10 to the power of 0. 20 of the students are not left-handed. That's our probability of failure. Since none of the students are left-handed, all must fall into this category, 0.90 to the 20th power. Plugging in our values will look something like this. Now when we work out the first portion, NCK, it comes out to 1. 1 times 10 to the 0, or 0.10 to the 0, which is also 1, times 0.90 to the 20th. If I multiply these values together, I end up with approximately 0.122, or 12.2% if we convert it to a percentage. Now suppose we wish to determine the probability that the student finds left-handedness in at least 3 students. That is, the probability of at least 3 which we can write using this notation, probability that x is greater than or equal to 3. We begin by setting up our formula. 20 students altogether, where 3 have the left-handedness trait, times our probability of success, raised to the 3rd power, times our probability of failure, raised to the 17th power, plus the number of students, 20, over 4, who have the left-handedness trait, times our probability of success, 0.10 to the 4th, times the probability of failure, 0.90 to the 16th. Now this formula will continue using the pattern. So the next would be parentheses 20 over 5 times 0.10 to the 5th times 0.90 to the 15th. You would continue all the way to the end until you obtained .10 to the 20th times 0.90 to the 0. We're not going to work this all out here because it's quite time-consuming. But you can do the complete binomial expansion, work out all the values, and the result you'll obtain is approximately 0.323, or 32.3%. We'll be working this out on the calculator shortly, and you'll see that it's a much more efficient and time-saving method for solving binomial probabilities. Suppose we wish to determine next the probability that 5 or 6 students have the left-handedness trait. In other words, p of x equals 5 plus p of x equals 6. We simply set up our binomial formula, 20 and 5 times the probability of success, 0.10, raised to the 5th power, times the probability of failure, 0.90, raised to the 15th power. Next, we add this to 20 and 6 times 0.10 to the 6th times 0.90 to the 14th. Let's work it out. Here you can see I've rewritten the same formula, and I've substituted my mathematical notation, parentheses 20 and 5, and I've rewritten it using the appropriate formula. By plugging these values into the calculator, you should obtain the following result. 0.04, or as a percentage, 4%. Next, suppose we wish to find the probability that our student finds left-handedness in no more than 7 students. In other words, the probability of no more than 7 is equal to the probability that x, our random variable, is less than or equal to 7. Setting up our formula, we'll start at 0, since we're interested in 0 through 7. So 20 and 0 times the probability of success to the power of 0 times the probability of failure to the power of 20, plus 21.10 to the 1st times 0.90 to the 19th. And we would continue in this fashion until we got to 7. 27 times 0.10 to the 7th times 0.90 to the 13th. We would then take our values in parentheses and rewrite them, substituting in the correct formula for NCK, and the result that we should get is 0.999, or 99.9%. Now this makes sense, because we can imagine that if the incidence of left-handedness in the general population is about 10%, the probability that we get no more than 7 students that are left-handed is going to be pretty high. So that 99.9% seems about right. Let's go back and take a look at finding these same probabilities using a TI-84 graphing calculator. What is the probability that the student finds left-handedness in none of the 20 students? Next, using our graphing calculator, we'll determine the probability that at least 3 students are left-handed. So, because we're looking at the at least case, the probability that at least 3 students are left-handed is equivalent to 1 minus the probability that 2 or fewer are left-handed. We'll set it up like this. In your calculator, 1 minus second key, distribution, which is above your variables key, then select option B, binomial CDF, and again we'll put in n, comma, p, comma, x. N is 20, p, probability of success, is 0.10, and x, because we're looking at the probability that the student finds left-handedness in at least 3 students, here we'll put in 2, because it's 1 minus the probability that 2 or fewer are left-handed, That gives us the probability that 3 or more are left-handed. This process may seem a little counterintuitive. It does take some getting used to. Basically, we're saying at least 3 is equivalent to 1 minus the probability of 2 or less. This comes out to 0.323 or 32.3%. Finally, let's look at the probability that the student finds left-handedness in no more than 7 art students. Again, we go to second, distribution. We'll select option B, binomial CDF. And then we'll type in NPX, which will be 20, 0.10, 7. Our result is 0.999 or 99.9%. As you can see, the calculator is much less time consuming and a bit more straightforward than applying the formula. But it's good to understand the process of the formula so that you have a better comprehension of how binomial probabilities work.